Okay, so the first definition you need to know is what's meant by a free oscillation. Well, a free oscillation is very simply as follows. It's if you displace an oscillator and release it, then it just kind of is left to its own devices and will oscillate. There's no external force kind of messing it around, and it's just going to do what it would naturally do. So if an oscillator is displaced and then released, it will begin to vibrate. If no external forces are applied, then it is a free oscillator. It'll oscillate at constant amplitude. That means if we were to draw a graph then of a free oscillator, then we would sketch out something which is going to be behaving as a simple harmonic oscillator, but it's just going to maintain the same amplitude and just keep doing what it wants to do at the frequency that it wants to do it. So for example, if I have a mass on a spring and I displace it and then walk away, it's just going to oscillate backwards and forwards. And if we ignore the effects of air resistance and damping, then it will just keep going. So let's look at the two most well-known examples of oscillators, of free oscillations, which is the simple pendulum and the mass on a spring. And we're interested in an equation for the time period of the simple pendulum and an equation for the time period of the mass on a spring and an equation for their natural frequency. By natural frequency, we mean the frequency at which it will oscillate if just left alone. Of course, that is what a free oscillation is. If you displace an oscillator and leave it just to do its thing, then it will just oscillate at its natural frequency. So that's just what the word natural means there. So let's start with the simple pendulum. And we know kind of what a simple pendulum is. There's a simple pendulum, like a bob on a string. And let's suppose it has length L from the centre of mass of the bob all the way to where it's swinging from. Well, we might therefore define its displacement, approximately speaking. I mean, it obviously goes in a kind of small curve as it oscillates, but we'll just define the displacement as that distance there between the bob and the equilibrium line. And well, it turns out that a simple pendulum only obeys simple harmonic motion when the angle is pretty small. In other words, if the angle gets too big, so if we displace it too much here, then it's no longer true to being simple harmonic motion. So this is only true for small angles, that these will actually behave simply harmonically. Well, remember the condition for simple harmonic motion. For simple harmonic motion, we have to have that the force is proportional to the displacement and in the opposite direction. I did that in the previous course. Well, it turns out that for a simple pendulum, the force is indeed, for small angles, is indeed proportional to minus x, and it actually equals minus mg over L times x. So m is constant, g is constant, and L is constant. Now, if you want to know why that is, then I've put an optional extra video in that derives that for small angles. But I won't include that in this video because in the exam you won't be expected to derive that equation. But do have a look at that optional video if you're interested. So, well, that gives us then an equation that tells us that we've got simple harmonic motion. I'll put a little asterisk and I'll put it up here and I'll say only true for small angles, because that's quite important. We don't want to forget that. And by small angle, you know, 15 degrees and lower, you're pretty good. You've got a pretty good simple harmonic oscillator. Okay, well, if that's the force, then we can write down an expression for the acceleration, because A is F over m, so we divide through by m and we get A is minus g over Lx. And then, of course, what that means is because it's a simple harmonic oscillator, we know that A is also minus omega squared x, where omega is the angular frequency, angular velocity. And so, so we can actually see from there that we've got a kind of identity here between g over L, gravitational field strength over the length of the pendulum, is equal to omega squared. So we can actually write down g over L equals omega squared for a simple pendulum. And then we just have to mess around a little bit to get the fact that the time period, remembering that the time period is 2 pi over omega, well, we can pretty quickly figure out then that the time period is going to be equal to 2 pi root L over G. And if you want to pause and check that for yourself, you'll quickly be able to see that. Well, that's a really important equation that's given on the equation sheet. And let's just see what it's telling us. It's telling us that the time period of a simple pendulum, as long as the angle's small, will be 2 pi root times its length over gravitational field strength. And that means we can go ahead and figure out the natural frequency, because we know, don't we, that there's a relationship between natural frequency and period. So we can say, well, the natural frequency is just going to be 1 over the time period. And if we do 1 over that, then we get frequency as 1 over 2 pi. And we flip it over, root G over L. So we've got a lovely equation there for the natural frequency of a simple pendulum. Isn't it nice? The mass doesn't matter. It's only the gravitational field strength and the length of the pendulum, as long as the angle's small, remember. So you can put as heavy a bob as you like on the pendulum, and it won't affect the time period or the frequency for a freely oscillating pendulum. But if you take it to the moon, then that will affect its time period and its natural frequency. So let's look at a mass on a spring and do the same thing. Okay, so a mass on a spring, well, this is kind of easier, and you do need to be able to derive this, the time period and natural frequency equation for a mass on a spring. It's a little bit more straightforward, of a more straightforward derivation. Well, for a mass on a spring, we know that fundamentally it obeys Hooke's law. So we've got that F equals minus kx, where k is the spring constant. Just bear in mind, sometimes you get systems in questions with involving two springs or something else which is springy and obeys Hooke's law. And the system as a whole is described as having a spring constant k. But you can just think of it in exactly the same way. So F equals minus kx, well, we're going to do the same process here. We're going to say, okay, so the acceleration is going to be minus k over mx. And because it's a simple harmonic oscillator, then we know that a equals minus omega squared x. So we can just say, aha, okay, well that means in this case, omega squared must be k over m. Yeah, has to be. So we can write that down. So omega squared equals k over m. And then we do a little bit like for the simple pendulum. We say, okay, well, because t is 2 pi over omega, and omega will be root k over m, then hopefully you can see, or have a go yourself, have a pause, that t is going to be 2 pi root m over k. Well, there we are. That's the time period of a mass on a spring oscillator, free oscillator. Good. And it means you can calculate, just knowing the spring constant and how much mass you've got on there, you can calculate it. And we can then carry on as before, and we can figure out the natural frequency. So, well, the natural frequency is just 1 over t, so it's going to be 1 over 2 pi root k over m flipped over. So that's it. So we've done it nice and quick there for the mass on a spring. And so just bear in mind that in the exam, they give you the time period equation. So they give you that one and that one for both, for simple pendulum and mass on a spring. They don't give you the frequency one, the natural frequency one. But of course, all you have to do is just 1 over the time period to get those. But questions do expect you to be able to use those and know what they're talking about.